So I'm drawing in a wave, and by wave, I mean something that periodically repeats itself. And so, what is a period? Well, a period is going to be on a wave, just mark a point, and when you get back to that same point again in the pattern of the wave, that is a period. In other words, period is going to be one cycle, and more specifically, the amount of time that elapses for one cycle. So let me say, let's pick on this peak right here and this peak right here. That is going to be one cycle. And so the amount, if I like think of this as the x-axis and this is the y-axis, the amount of horizontal distance that's covered in one cycle is going to be the wavelength. I'm going to say that again. When you have one cycle, that is, you get to right back where you originally were. The wave repeats itself. The amount of horizontal distance that's been covered is the wavelength. So you could probably imagine that if you have a wave that is much more squiggly, like something like this, that's a much shorter wavelength than what you see in the red. And so there's a relationship between wavelength and frequency. So with frequency, we need to think about how frequently the wave repeats itself. So when the wave goes through one cycle, we call it the period, and we give it the symbol T. And that period is the time for one cycle. And so for simplicity, let's say that for the two peaks that I've marked on this red wave, let's say that 1 second elapsed from peak to peak. And so the units of period are seconds. And so if 1 second precisely elapsed between peak to peak, the period would be 1 second. If half of a second elapsed from peak to peak, the period would be half of a second. So again, the period, which is in units of seconds, is how much time elapses for one cycle of the wave to transpire. And so the period is related to the frequency. Quite simply, if period is the amount of time for one cycle, the frequency is going to be the reciprocal of the period. And so the frequency is going to be the number of cycles per second. And so look back at the red one versus the orange. The red wave doesn't have as many cycles per second as that orange one does. And remember, the wavelength of the red one is longer. Like if I wanted to think about the wavelength of the smaller one, look at that compared to the red. The wavelength is shorter for the orange wave, which has higher frequency. So there's an inverse relationship between the size of the wavelength and the frequency. The higher the frequency, the shorter the wavelength. The lower the frequency, the longer the wavelength. And one other thing to think about is the wave can also be thought of as having a velocity. And so let's say that the wave pattern is moving along at some velocity v. And so now we can actually express the wavelength in terms of the wave velocity and the period, because we know that lambda is going to be the distance covered over one cycle. And we know that the period is the amount of time that elapses over one cycle. So if we know how much time elapses over one cycle, we can multiply that time by the velocity of the wave itself, and that'll tell us how much distance has been covered, which will give us the wavelength. So in other words, lambda equals the amount of distance per time covered by the wave multiplied by the amount of time for one cycle. Because remember, the wavelength is the amount of distance for one cycle. So you can think of it like this. The unit analysis, the wave speed is going to be meters per second, and the period is going to be in units of seconds. And so the seconds cancel, and you get units of meters, which is precisely the unit of a wavelength. So if we know the amount of time that elapses in one cycle and we multiply it by the wave velocity, that's going to tell us what the wavelength is, because the wavelength is how much distance was covered in one cycle. Just to review, the wave is periodic motion. It repeats itself. And for one repetition, i.e. one cycle, we say that the amount of horizontal distance that's covered is the wavelength. We say that the amount of time that's elapsed for one cycle is the period. And then we can think of the frequency as the reciprocal of the period. In other words, if the period is the amount of time that elapses in one cycle, then if we take the reciprocal of that, we know how many cycles there are per second. So for instance, let's say that going back to the red, remember I said hypothetically from peak to peak was 1 second? Well, that frequency would be one cycle in 1 second. In other words, it would be 1 hertz. And the units for frequency are given in hertz. Well, let's say instead that to go from one peak to another peak, it was only half of a second. So if it was only half of a second, then the number of cycles in 1 second would be 1 divided by 1/2. And that would actually be 2. You would be able to compute 2 cycles in 1 second. So when you think of higher and higher frequency, think of more and more of the orange wave, like the much squigglier one, because there's many, many more cycles per second. And so when you think of high frequency, lots and lots and lots and lots and lots of repetitions. And when you think of low frequency, fewer and fewer and fewer repetitions. Turns out for sound with frequency, when you think of like high pitch, it's going to look more like that orange. It's going to have a much higher frequency. Whereas if you think of like bass is going to be much deeper. Bass is going to look more like that red wave. It's going to have a lower frequency. So high frequency, think of like treble. Low frequency, think of bass. And whenever you think of frequency, you should have a picture in your mind of what the wavelengths might look like relative to each other. So now that we've got the anatomy of the wave, I want to show you how, if you have two waves, how they can be added by superposition. You take wave 1 and you add its amplitudes to the amplitudes of wave 2. So I'm going to do my X and Y again, and I'm going to have a wave. And so let's say that right here, Y equals 4. So what I'm going to do now is I'm going to introduce another wave. And we are going to introduce another wave that is perfectly in phase. And by perfectly in phase, I mean all of the peaks match all of the peaks, all of the valleys match all the valleys. These are two waves here, red and blue. They're perfectly in phase with each other. So what happens is you're going to have the addition of the amplitudes. And so if both the red and the blue have amplitudes of y equals 4 at their peaks, then the resultant wave is going to be 4 plus 4. And so the resultant wave, I ran out of room here, so let me make it a little bit smaller so we can get things to scale. So my apologies about that. So let's do something like this. And then blue is, so those are in phase with each other. And so let's say again, y equals 4 for both of these. So for this point right here, the resultant wave is going to be the amplitude of the red plus the amplitude of the blue. And that's going to be 4 plus 4. So that amplitude is going to be y equals 8. And so then say down here, y equals -4. And so amplitude -4 for red, amplitude -4 for blue. So you're going to have y equals -8. Where it crosses the x-axis, you have an amplitude of 0 for blue and 0 for red. So it's also going to be 0, 0 plus 0, 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 0. We have another peak and peak lining up, 4 and 4 again. So that's going to correspond to 8. And then we have another valley, -4, -4, -8. And then another peak. So my resultant wave is going to look much bigger than either of the two waves that were superimposed to make the resultant wave. So this is when the waves perfectly constructively interfere with each other. They line up, so the peaks add up to make even larger peaks, the valleys add up to make even larger valleys. But let's look at a situation where instead we have the waves completely out of phase with each other. Wave. And now what I'm going to do is do a wave that is 180 degrees out of phase with the first wave, which is to say that the valley of the red wave would correspond to a peak of this blue wave that I'm drawing in. And then a peak of the red wave would correspond to a valley, and a valley to a peak, and a peak to a valley, and so on. So imagine we've got a wave that looks like this. So what I've drawn there are two waves, the red and the blue, but now they are 180 degrees out of phase with each other. The peak of one corresponds to the valley of another. So again, let's say that y equals 4 is the amplitude. And so down here would be y equals -4. Well, let's see what happens. Like, for instance, when we have a peak right here, that corresponds to a valley right here. And so you would have +4 and -4. And so what would happen when you add those two amplitudes together? +4 and -4 is 0. Or what about right here? This would be +4 for the red and -4 for the blue. What happens when you add the amplitudes there? It's 0. What about when they cross over? Well, 0 and 0 is 0. 0 and 0 is 0. And now the blue is at a peak again, +4, but this is at -4 for red. So what do you have? 0. So you should probably notice a trend here. The addition of two waves that are out of phase by precisely 180 degrees. I'll give it some color here. The resultant wave is just a flat line. It's 0. These waves have completely constructively interfered with each other to where they've canceled each other out. The resultant wave is no wave if you have two waves that are 180 degrees out of phase with each other. So I want to show you an application of this idea. So imagine you have a situation where there's going to be two speakers. Let's say there's a speaker so imagine those are two speakers, and imagine that there's a person that is listening to the two speakers where they are completely in the middle, such that the distance between the listener and each speaker is the same. So essentially you have like an isosceles triangle. And so you can imagine that there's waves that are coming out of each speaker. Now, let's say that the wave velocity of one equals the wave velocity of two. And so then if the waves are traveling at the same rate, and we are going to assume that D1 and D2 are the same distance, so you can imagine they're standing right such that there's an equal distance between the person and each speaker. Then if the waves are in phase with each other, when they leave the speaker, then they're going to go through a certain number of cycles, as you can imagine. But remember, if they were in phase with each other, when they leave each of the speakers, if they're traveling the same rate, i.e. their velocities are the same, and the distance is the same, then you should expect that when they get to the listener, they're still going to be in phase with each other. The same amount of ground has been covered, the same speed has covered that ground. And so wherever the wave was when it precisely left one of the speakers, for each of the speakers, it's going to be in the same place when it gets to the observer. They're going to be in phase with each other. And so if they're going to be in phase with each other, then it's going to be like the example I showed where if you have the peaks aligning with the peaks and the valleys aligning with the valleys, you get this resultant wave that has an even bigger peak and an even bigger valley. And so where that person is in the audience listening to these two speakers right now, they're going to get a loud volume. It's going to maximize when you have two speakers delivering music to you, you got a loud spot where that person is standing. But here's the thing. Let's say that maybe you weren't lucky enough to get a seat in the center. So let's say that instead you are over here. All right. So now you've got some distance D2, and you've got a different distance D1. The reason that I'm calling it D1 and D2, I'm assuming that this is speaker number 1 and this is speaker number 2. So I hope you can see that with the new position in the audience, you've got a discrepancy now in the distance between speaker 1 and the listener and speaker 2 and the listener. And more specifically, that difference in distance is what you see me marking in black here. That is extra distance that speaker 1's wave has to travel to get to the listener versus speaker 2. And so here's the key. There's a difference in path length. The path length between speaker 1 and the person is greater than the path length between speaker 2 and the person. So the question is, given that extra path length, how does that extra path length vis-a-vis the wavelength of the wave? Like, so for instance, let's say that so the green is the wave traveling that extra distance. And so what I have right there is that the wave, it has a peak, a valley, a peak again. And so that would be 1.5 wavelengths. Let's draw it even more simple. Let's say that so let's say that extra distance that has to go between the first speaker and the second person is going to be precisely 1 wavelength. So imagine for a moment, in this extra distance that it has to travel, that extra distance is precisely 1 wavelength. So if that extra distance is 1 wavelength, even though the waves from the first speaker had to travel farther, since the extra distance they traveled was precisely 1 cycle, then they're still going to arrive at the listener in phase with each other. Because remember, these things repeat themselves. So even though the first one had to go a little bit further, the distance further it had to go was precisely a cycle. So they're still in sync with each other. So if that difference in path length is 1 wavelength or 2 wavelengths or 3 wavelengths or 4 wavelengths or 5 wavelengths, the waves are still going to be in sync with each other. And so when they constructively interfere, you're going to hear something. But what if instead you had a situation where it was only, say, half of a wavelength? And so lambda over 2. In that situation, because of the extra distance that was traveled, what were originally 2 waves in sync with each other, because the other one had to travel an extra half wavelength, it's now out of phase with the second speaker. In other words, its valleys now correspond to speaker 2's peaks and vice versa. And so remember what happened when the waves are out of phase with each other by 180 degrees? They have complete cancellation. And so that would be like a dead spot in the auditorium where you would be listening to the concert. It certainly wouldn't sound as good as if you were in that first position in the center. And so you can probably imagine that based upon different positions, you're going to have differences in path length between two or more sources of waves. And so then the issue becomes, how do those differences in path length measure up to whatever the wavelength of the waves is? And if the difference in path length is an integer multiple, in other words, 1 wavelength, 2 wavelengths, 3 wavelengths, 4 wavelengths, then you're going to have constructive interference where the sum of the wave is greater than the individual waves themselves. But if you have a situation where the difference in path length is half of a wavelength, or 3 halves of a wavelength, or 5 halves of a wavelength, or 7 halves of a wavelength, now, because of that extra distance, the waves are now out of phase with each other when they get to the observer. And that's when they cancel each other out. So just to kind of make a little bit simpler picture, just imagine 2 wave sources, and at some point where the distances are equidistant, you're going to have a maxima. And then that maxima is going to have a minima on both sides. But then you're going to have, so I'll call that max 1. You're going to have a secondary maxima on both sides. So what that corresponds to is, for the central maxima, you have precisely the same distance. And so if the waves are in sync with each other and they're traveling the same velocity, they're going to stay in sync with each other, and it's going to maximize how much they add up. But then if you think about, say, this location right here, now the distances are not the same. There's going to be some difference in path length. And so that minima is going to be when that difference in path length is half of a wavelength, which would mean that they would be 180 degrees out of phase with each other. They'd cancel each other out. But then there's going to be another time where, even though one wave travels farther than the other, so this location right here, so there's definitely extra distance that has to be traveled. But let's say that that distance corresponded to 1 wavelength. So it was just 1 wavelength. If it was just 1 wavelength, then even though it had to travel farther, it's still going to be in phase at that secondary maxima. In other words, you're going to have constructive interference where the waves aren't canceling each other out. And the same goes for the bottom. So there's going to be a place where there's a difference in path length. Now it's from the top speaker. If that difference in path length is just half of a wavelength, then even though the waves might have been in phase with each other at the start, now because the top speaker wave has to travel 1/2 extra cycle, now it's 180 degrees out of phase, and so that you would have a dead spot at minima 1. But then there's also going to be a situation where you move further down, and imagine that there's a difference in path length. If that difference in path length is precisely one wavelength, then even though it had to travel extra distance, the amount of distance it traveled is precisely one cycle's worth of difference. And so they're still in phase with each other. And so they still constructively interfere at maxima number 2 in a way that isn't destructive like at the minimas. And so you can imagine that there's alternating regions of loud spots and dead spots in the auditorium. And this all comes down to how waves constructively interfere with each other and to what extent the peaks align with the peaks and the valleys align with the valleys. Now, I'm just giving you the extreme examples of when they're perfectly in phase or 180 degrees out of phase. But you can imagine that there's all sorts of combinations of when they're kind of in phase and kind of not in phase. And so that means that at different parts of the room, you're going to have different constructive interference of these waves based on the fact that there's differences in path length, and therefore, based on what that difference in path length is, there's going to manifest differences in the phases that the waves are in when they finally do crash into each other.